Hello and welcome to section 6.4. This will be video 1 of only one video for this section. In this section, we will be looking at the inverse trig functions, and right triangles. So up until now, we've been given a measure for theta. Theta is 30 degrees, theta is 60 degrees. And from that, we were finding the other lengths of the sides of a triangle. Well, now we're going to be given the sides of the triangle and kind of go in the reverse process. So for example, let's say we wanted to find theta for the given triangle. It's a right triangle. One side is 10, the other side, the hypotenuse, is 50, and the angle theta we're trying to find is this small angle down here at the corner. Using our trig functions, what do we have? We have opposite from theta, and we have the hypotenuse. So opposite and hypotenuse would be what? That would be sine. So using these three pieces of information, we can set up the following equation. Sine of theta is opposite, which is 10, over hypotenuse 50. So now at this point we just need to solve for solve for theta. So if we simplify the right side, we get sine of theta is 1/5. And now remember, all of these trig functions are just that, they're functions. So for example, if we have x squared is equal to some value, what do? We use the inverse function. We use the square root. So same idea here. So actually what we're going to want to do to solve from this point is I want to take the inverse sine function of both sides of this equation. So when I do that, the sine inverse and the sine function essentially cancel each other out, just like square root and squared. And then on the right, this is where you're going to use your calculator. You're going to do 1 divided by 5, and then do the inverse sine function. And this should give you that theta is approximately 11.5 degrees. So again, it's just the reverse of the process that we've been doing to this point. Grab an eraser. So using this, we can also do an example like the following. Let's say, as an example, we want to find all angles between 0 degrees and 180 degrees, satisfying sine of theta is equal to 0.4. So this is the part we're concerned with. If we do the same thing we just did, so we take the inverse sine of both sides, this gives us that theta is approximately 23.6 degrees. Now, that tells us what? So that tells us that if we have our xy coordinate system here, that the angle in here when sine of theta is 0.4 means this degree is roughly 23.6. But if we think back to our reference angles, it also means what? It means that the angle over here would also satisfy sine is equal to 0.4. In that case, we would do what? If we know that this angle in here is 23.6, then the bigger angle, grab another marker, then this bigger angle would be what? It would be 180 minus 23.6. And if we do that math, that means that this is roughly 156.4 degrees. So between 0 and 180 degrees, we have two situations where sine of theta is equal to 0.4. It's when theta is 23.6 degrees, and it's when theta is 156.4 degrees. Lastly then, within calculus, and to be totally honest, also within this class, we're going to be dealing a lot with functions that look like the following. So we're going to have expressions like cosine of sine inverse of x. So again, we've dealt with some of them like this. We've had a value in here, and then we had to figure out what this value was first, but usually it was the same function. So sine of sine inverse of, I don't know, pi over 6, something like that. But now when we have this situation where we have two different sort of functions, we'd have an example like the following. We want to find cosine of sine inverse of 3/5. When we have problems like this, and then actually once they get a little more complicated, it'll be the same process to solve. The first thing we're going to do is draw a triangle. This should always be the first thing you think of when you see two functions where one is an inverse function, and the other is just the regular. First thing you should think of, okay, I need to draw a triangle for this problem. After we draw the triangle, we're going to label the sides using the information inside the parentheses. And then lastly, we'll determine the value of the function defined. So for example, once we build this triangle, then we're going to figure out the cosine from this triangle. So what I'm going to do is I'm going to call all this information inside the parentheses equal to theta. Not even going to worry about the cosine for now. So if I just use this, I get what is an equation? I get theta is equal to sine inverse of 3/5. So now, if I want to get rid of this sine inverse function, what do? Well, I would take sine of both sides. So that gives me what? That gives me sine of theta on the left. The sine and sine function essentially cancel each other out again, and I get 3/5. So now I'm going to draw this triangle. I'm going to label one of the angles equal to theta. So if here's my theta, based off of this information that I just generated, which is essentially step 2, I guess I sort of did that reverse. Draw the triangle first, then calculate this information. So now I'm going to take that sine of theta is equal to 3/5. So we know in terms of our trig ratio, sine of theta is what? Sine is opposite over hypotenuse. So that means that sine of theta is opposite, so from that theta opposite over hypotenuse. So now, if I rewrite what I was originally asked for, what do I have? I'm going to get rid of this information inside and just replace it with theta. So what I'm really being asked for is what is cosine of theta? So cosine, again, with our trig ratios is what? It's adjacent over hypotenuse. So I don't have the adjacent side here, but I could use Pythagorean theorem. This is also what's known as a Pythagorean triangle or a Pythagorean triple. So if we were to do the Pythagorean theorem, a squared plus b squared, so let's assume we don't know this, we'll call it b squared. So a squared, so 3 squared, plus b squared equals the hypotenuse squared. So 9 plus b squared is 25. If I subtract, I get b squared is 16. Take the square root, so this side here, b, would be equal to 4. So therefore, cosine of theta, or cosine of sine inverse of 3/5, is just equal to adjacent over hypotenuse, or in this case, 4/5. And that's it. So that's going to be the process every time. We draw ourselves a triangle. We redefine what's inside the parentheses in order to give us a trig equation. And then we replace what's inside with our value of theta or phi or alpha or beta, whatever variables you choose to use, and just figure that from the triangle we just drew. And in this case, the answer would be 4/5. All right, so I mentioned this is a Pythagorean triple. I'll give you guys 3 of them. Probably put these on your cheat sheet. Sometimes it can save you a little bit of time if you're not having to do the Pythagorean theorem every time on these triangles. So there's basically the 3 we're going to look at here. So these are Pythagorean triples. The first one, and we just saw it, it's a right triangle, and it's 3, 4, 5. So you may have even heard of this before, a 3, 4, 5 triangle. That's a Pythagorean triple. The second one is 5, 12, 13. So if the 2 legs are 5 and 12, the hypotenuse is 13. And then lastly, 8, 15, 17. So these all have exact lengths for sides. They're known as Pythagorean triples. You can also have combinations of it. So let's say on this one, if I double every side, what do I get? I get 3 doubled is 6, 4 doubled is 8, 5 doubled is 10. So using the idea of like similar triangles from geometry, if we just double all the lengths, it is also a Pythagorean triple, and that would work for any of these. Okay, so that's it for 6-4. Fairly short. The biggest thing was this last idea of finding these functions when you have like 2 different trig functions, one an inverse, one a regular, and using this process of drawing the triangles and solving it. So thank you very much. We'll see you in the next video.